So, hello. I'm just going to be giving kind of like a high-level overview uh, of like what FHE is, similarities and differences between like ZK for privacy versus using FHE, where they overlap. Um, yeah. So, I mean, yeah, feel free to just, I guess, chime in on anything since it's a, if any questions or anything. But yeah, like so just quickly, what is sort of like FHE? It's just kind of like this concept, sort of conceptualizing it as the ability to sort of like run an operation, apply logic, whatever you want to call it, over like an encrypted field without having to decrypt. So you can think about it like usually kind of hashes are sort of like indecipherable. So being able to run arithmetic expressions over these, allow us to kind of avoid having to leak any of this information to like a server, a third party, or basically a prover. It could be anybody who's kind of handling this computation. So as you see here, you can pass in, essentially you can run this function, but instead of running the function on like the plain text values, you're essentially running this evaluation um, on the ciphertext themselves. So if you think about it, you basically can like add two numbers together privately. Okay, yeah. So what is this FHE new buzzword that people are throwing out? FHE stands for Fully Homomorphic Encryption, which is just sort of like, it's kind of just a fancy technical name of being able to run, like arbitrary operations on an encrypted field. So the concept of fully homomorphic encryption is like relatively new. Again, like the idea of homomorphic encryption in general has existed for a while. Homomorphic encryption is kind of, you can think about it like what you do to one field happens to another field. Sort of what you do to X happens to Y. There should be a correlation there, a direct correlation, except in this case, like the plain text, what you do to the plain text should affect what happens to the ciphertext. Yeah. Oops. Oh yeah. So like a quick overview of like FHE is the new ZK. I mean, that's not necessarily true, but I just kind of mean it in the sense where like FHE is sort of kind of where ZK was maybe like 4 or 5 years ago. You're starting to see a few projects pop up. There's nothing really in production. It's still kind of more of a concept. Um, I think from a high level, most people still haven't like fully heard of FHE or what it can do. But here's a quick like timeline and like sort of like rough overview of sort of the different schemes and the history of FHE. So privacy homomorphisms have existed for a while. It's included in things you probably heard of like RSA, et cetera, which I guess is a form of homomorphic encryption to some degree. But for a while, and some seminal works were released in the 70s, as you can see here. But for the most part, for decades, like people were kind of just fumbling around with partial homomorphic encryption, which is kind of the ability of being able to do some things, but not entirely. So, it runs into problems. For example, like homomorphic encryption uses this concept of like, it's like noisy encryption. So you can kind of think of it as like you're adding lies into the truth, sort of, like I guess a metaphor of that is if you're playing like poker or something, you can't just be honest every single time or someone's gonna know you're lying. But essentially, when you do these numbers, right, like you're taking these two encrypted numbers and you're adding them, you're subtracting them, you're dividing them, you're doing whatever you want, really. Eventually, you're going to kind of hit this noise threshold because to the point where you can't decrypt back to the plain text. And so to solve this problem, this guy, Craig Gentry, came up with this concept called bootstrapping. And bootstrapping was essentially the ability to sort of reset the noise so that you could do like arbitrary computations. So at least in terms of a proof of concept, it wasn't scalable at the time. And, debate is still how scalable it is. But in theory, there was a proof of concept that we could actually run these like complete operations over ciphertext. Um, and as you can see, there's a bunch of different branches that kind of forked off from these. For example, there's this branch here, which is called like the leveled scheme branch. Some people say that this is better for machine learning, but I guess that's kind of a contested field to some degree. But basically, it's an approximate scheme to some degree. And then we have TFHE, which is what is currently used mostly for like blockchain implementations, specifically, which is kind of like this like fast bootstrapping, which is like essentially resetting the noise programmatically via, most of the time after each operation. So, like a quick, I'll try to, go through this, but basically from a high level, like FHE and ZK both provide some level of privacy. ZK is more scalable than FHE now, is currently. However, FHE is scaling pretty quickly. I mean, at least I think FHE is scaling, faster than I think people are aware of. I think, sometimes you'll talk to people that were in the space and they'll say like, oh, I was interested in FHE in maybe like 2020, and then it's very different now. There's a lot of research and production being done in hardware. Um, acceleration, but from a high level, the main issue with ZK for privacy is that you can't really construct a composable shared state. You could try doing some sort of rounds, and there's ways to sort of get around it. But basically, since the states need to be handled off chain, and then that privacy isn't really composable, it kind of sort of limits some of the options that you have for actual private computation. Because at the end of the day, ZK proofs tackle the privacy problem by keeping the committed data of the proofs on chain of the correct computation. Um, but this data has to be known to plain text. For example, if you try to look at like something like PSC Macy, for example, like, one of the problems they're running into for like private voting using ZK is that at a certain point there has to be essentially this trusted coordinator that has to decrypt the votes in order to actually tally them, because how else are you going to run an operation over this encrypted field, the ciphertext? Um, so ZK is decent for privacy if it's just for a single party, but like once you try to like scale this out into multi-party applications which require a shared field, that's when you start to run into some issues. But from a high level, you can also consider it that like ZK and FHE are kind of trying to solve two problems, although to some degree ZK is still kind of marketed as like a privacy technology. Um, some will say maybe that's because like FHE, like people didn't know about it, or it's just it was like really not feasible. So there's still not really a mainnet for anything. But yeah, to me, ZK is kind of trying to solve a very different problem, right? It's sort of like the off-chain verification, and then you're kind of verifying the correct execution. Like, sure, you can keep the inputs private, but like, how far does that really go? And then FHE is trying to solve the problem of like kind of end-to-end encryption privacy, which is basically like actually doing each of these state transitions. Each of these values can remain private. They can remain, so if you have adversarial data sets. Um, yeah, so there is a lot of potential between FHE and ZK kind of working together. Like I said, I think to its nate by its to left to its own devices, FHE doesn't necessarily provide the guarantees of correctness in terms of like what happens. So you can kind of think of it as like FHE is sort of a way of doing things, and ZK is sort of a way of verifying things. So like, why not verify that a certain way that something was done in a certain way? So basically, just like there's you could use something like VFHE, which is sort of like this verified FHE, which is like using a snark, for example, to guarantee the integrity of the computation, but require the plain text knowledge of the data, which is computation proven correct. And so these can kind of, work together to try to solve like these privacy problems that we're solving. And again, just from a high level, if you like zone out, don't take anything from this talk, but like just the one thing to remember is that from like the issue with ZK for privacy is at the end of the day, right? You can't really run a computation over a shared private state. Of course, I guess you could include some sort of other method, such as like some sort of MPC secret sharing or something. But like at the end of the day, that still require round interaction versus FHE. You can kind of advance a state over these private fields and operations without necessarily have decrypt, right? Because if you don't use something similar to FHE that allows you to run these operations over an encrypted field, you're basically decrypting, which means you're leaking plain text to memory, which generally speaking is a honeypot for vulnerabilities, etc. And the benefits of ZKP for privacy over FHE, I mean, I suppose you could make the argument that ZK allows for sync verification versus FHE. The operations themselves have to happen sequentially. I mean, there's research being into parallelization, but generally speaking, state construction, again, like ZK has to kind of happen off chain versus, FHE on chain. For example, like a FHENIX, the architecture basically allows you to have like these multiple VMs, and they can both be verified, broken down into a format that can be interpreted by the laws of verification, hence becoming like the L2 verifying state transitions. And so like from a visual perspective, I kind of think of it as like ZK for privacy is sort of like an image. You can kind of like verify that like one instance of something was kind of done, a certain computation was done um, privately. But like trying to have some sort of like iterative process, having the state is usually going to require some form of like decryption, and then adding to the state, and then encrypting that again, et cetera, and having multi-party. How are you going to do that synchronously is kind of a is a difficult problem that also needs to be solved when you're involving these operations. Versus FHE is kind of like a reel of a movie where it's kind of like you can sequentially like append to this. You can go in, you can check like okay maybe frame 4 the pebble's like too low. You can edit it, which is sort of like the benefit of the expressiveness over private field that you're guaranteed with FHE. And so like another visual representation of like how these like ZK applications might actually work versus like a fully private application using FHE. And I avoid using the word like fully private because like what's ever fully private, but um, essentially you're allowing people to write to the similar shared state versus in ZK. Like think about this, like I'm sure we've all heard like private DeFi, MEV, like these like buzzwords. Like we ever actually like look at how like these private DeFi like ZK uh projects are working. I think most of them are kind of operating at like the like it's a time lock sequencer. It's like some sort of batching. It's like okay, even something like even some projects are using like additive homomorphic encryption for like the batch purposes. But like if you don't have division, how are you going to handle things like uh slippage, et cetera. And like that doesn't even tackle the real problem, right? Because it's just like fancy footing away around sort of like just multiple ways of doing a similar thing versus like with FHE, you're actually kind of allowed to like hold like a shared private state for something like, for example, like an AMM, right? If you want to add liquidity and you want each person to have like a shared fragment of the state, right? Even if you try to do something which like, I don't know, boils down to like some sort of like secret sharing at some point where you're all kind of attesting to the same private field, shared private field, like what are you going to do? There's like 10,000 people depositing liquidity every single time someone wants to update state, you're going to do a round. Like that's just not very feasible, not really something that can really be handled in like state channels to some degree. So that's kind of like one of the benefits of using FHE where like ZK is kind of just like, um, I don't know why people keep pushing that. I mean, maybe it's just because like FHE isn't feasible. Maybe this is just completely, I mean, maybe it's just a theory, but I mean, conceptually, if that makes sense, those are sort of like one of the benefits that you would get using FHE for privacy, where like you end up kind of just doing the similar thing over and over again with ZK. But I'm painting with a broad brush. That's not necessarily applicable to every situation, but also applies to games. Something like uh, that requires like a large shared private state, for example, if you have like 1,000 players that need to contribute to some sort of shared board. Again, think about how this would have to work in terms of interaction, because FHE, these operations to advance the state can be happened, non-interactive in an uninteractive way. So what are the alternatives to FHE and ZK methods? I don't necessarily think this is like the most practical use of like playing with FHE. It's sort of just like a hackathon project that someone submitted to us, but basically it's sort of using like FHE for the verification process. So from a high level, I won't go into too much of this, but just if you think about the process of like the ZK verification, here's an example. Again, won't dive in too deep into this, but there's kind of a reason why it's difficult to sort of do a lot of this like verification over FHE, for example. With FHE, like verify FHE in a zero using zero knowledge proofs. Right now, we're just at FHENIX we're using optimistic verification just because of the proof overhead size, which is one of the main bottlenecks. But I'll get into that a little bit later. Here's just kind of an example of I'm sure some of us are familiar with the concept of a pairing function. See these types of loops, and this division operation would just be very expensive in FHE. And so we are able in this project, the link I showed earlier, if you wanted to look more into it, but basically it's kind of just running very simple operations like as some sort of verification, um, uh, like ZK verification of this FHE operation. But one of the benefits of running it this way is that we're actually able to keep the output of the proof private, so you don't actually know if it was true or false. Obviously, this isn't succinct verification, so I mean, how practical this is, I'm honestly not sure. It's more of a toy. The other concept is kind of verifying the FHE operations themselves versus via ZK, like end to end. So basically, here's another quick example of some research that's kind of been done. But basically, you're kind of passing in two encrypted numbers, and then you're performing this operation here, which is like, something very simple, just like adding two numbers, which is basically like ciphertext A, ciphertext B produces ciphertext C, which is a sum of ciphertext of the plain text values of ciphertext A and B. Um, yeah, so something a little bit more practical that the other two are kind of just like random, not like just sort of like proof of concepts. But basically, you can use something like a zero knowledge proof of plain text knowledge, or proof of knowledge essentially, to ensure that the ciphertext is valid, that the basically that the contents of the plain text and the format of the ciphertext is correct because like a lot of FHE VMs are kind of predicated on the fact that the operations themselves. If you're verifying the state changes via the operations themselves, you can do this on the assumption that both of the ciphertexts that you're operating on are valid ciphertexts. And so from there, um, you can take it to extra steps. And if you want to look, Zama and the PSE have both looked into different implementations of trying out this concept in practice. Another thing is verifying FHE bootstrapping via a snark. So another link if anybody's curious, but so bootstrapping, if you remember before, is kind of this concept of how we were able to move from partial homomorphic encryption to fully homomorphic encryption, which kind of entails the ability of like resetting the noise threshold. And so from here, and actually is like one of, if not like most of the time, is the most expensive part of like the whole this FHE process, if you will. Besides the NPC decryption, but that's kind of a different topic. So basically being able to verify stuff like this is pretty cool. It's kind of like some would say it's like the first step of like many steps that eventually allow us to have something like an FHE rollup that's actually like ZK verified versus like optimistically verified. But yeah, this is pretty interesting. The overhead's still very high. Um, yeah, and like going off of the overhead costs, like yeah, that seems great. And like, okay, theoretically it's possible. But like, it's gonna take 20 minutes to do a single bootstrap. So like you need to do one of those for every single operation. And if we're trying to do thousands of them per transaction, like that's just not very feasible. But we also have to consider that, back in 2009, doing like one basic, like not even yeah, just doing one basic like FHE operation basically took, 20 minutes, an hour, depending on what you were doing, and now we can do thousands of them in a second. So the technology is speeding up pretty quickly. Maybe we further research like anything. It's probably going to be some better research on like the proof systems, software, but also potentially like specialized hardware. Yeah, and so just like a really quick like simple example of like personally how I kind of like transitioned a little bit from like into FHE. So sort of like before I was personally working on like on-chain gaming operating system, and I wanted to figure out how to make a combat engine essentially. I don't know if anyone's familiar with Pokemon. But Pokemon is like kind of this game where you have synchronous inputs and you advance the state. Sorry, you have asynchronous inputs and you advance the state synchronously if it's like a PvP game. So in Pokemon, sometimes there's interactions, like if one player uses like Focus Punch, the other player hits the player, and then that causes the game state to fork and branch in different directions. Such as if someone uses Protect, someone doesn't Protect, there's like speed, like Quick Attack is a speed priority, but I won't get too much into that. Basically, ignore this. There's a simple example of like rock paper scissors, basically, where if you think about the concept of doing rock paper scissors on chain, basically you're gonna have to somehow encrypt or hide the first value where there's like some sort of pre-image nonce, whatever you want to call it, a key, I don't know. But like basically the first input has to be encrypted, or else the second player is basically just going to query whatever move the first player made and kind of just backrun them and win. So I looked into ways to try to do this on chain, and I was basically um, I first started off with implementation using ZK. And like so with ZK, kind of like what I was saying, you sort of have to commit your move, but then you also have to commit some sort of a proof of your move to basically be like, yes, this is the move I made, it's private, but like I need to submit a proof that I can verify later at a certain point once it's time to advance the state. Uh, and sort of if this now the second player is going to make this public attack, which I mean can be in plain text, it doesn't really matter. And then the third player is essentially going to have to um, uh, and then the original player is basically going to have to verify their proof one more time. That the move that they actually locked into is the move that they locked into and can't cheat. And are not just saying like, oh, I did rock, but now I see you did paper, so now I'm changing my move to do scissors. Like, can't do that. And then you can actually advance this game state after the proof is verified. And some would say that like actually you might have been better off just using some basic commit reveal scheme here. Um, Okay, weird. But how it works with FHE is actually a relatively simpler process where you're essentially just kind of like committing your move via ciphertext, uh, encrypting your value and submitting it on chain, and then the second value can just happen in plain text, and essentially the original value can be compared to the original value via decryption or via some sort of homomorphic comparison, and then the game state can essentially branch from there. Um, yeah, so basically that's just kind of a quick example of like how encrypted state can operate. And this is a very simple example where you're not actually having any operations. It's really just like a commit of encrypted data on chain, private data. I guess you're not supposed to say private because whatever. But yeah, if you have any questions, yeah, please contact or check out FHENIX if anyone's interested. It's like FHELP, we just released our testnet yesterday. So yeah, cool. And that's well, yes. Yeah, if anyone has any questions. This one? Thank you.